To finish off this chapter on the central limit theorem, we will look at how this theorem is extended towards populations that are not normally distributed. And also, crucially, we will look at the limitations of this theorem, where it breaks down. Now remember that in the previous lesson, we introduced the sample statistics distribution. This was obtained by collecting a very large number of samples of the same underlying population. And then for each sample, we compute a specific statistic, for instance, the mean. Then if we collect all of these statistics of these samples together and we visualize it in a histogram, we can see the sample statistics distribution. And it is about this distribution that the central limit theory says that it will approximate a normal distribution. And additionally, it will be centered around the value that approximates the population statistic extremely well. Now we ended on a note that these sample statistics distributions are normally distributed only because the underlying populations are also normally distributed. But this touches on one of the most powerful aspects of the central limit theorem, namely that it extends beyond populations that are normally distributed. For instance, take a look at this one. Here we see clearly that the underlying distributions of the populations are not normally distributed. Here we have a Rayleigh distribution and here we have a uniform distribution. Nonetheless, if we go through the same procedure, then we see that the sample statistic distributions are normally distributed. Now you don't have to take my word for it, because we can of course simulate it by going through the same notebook cell as before. And in this way, you can play around with it yourself. So let's look at the code. Now, what you see here is the exact same notebook cell from the previous lesson, where we simulated the central limit theorem for two populations that are themselves normally distributed, and we generated them right here. But now we want to use different populations that are not normally distributed. And this is where this block of code comes into play. Here we see that there are different populations that we can generate, each with a different distribution. We have the uniform distribution, the exponential distribution, and the Rayleigh distribution. Now, where all of these distributions come from and which real-life scenarios they represent, we will see in detail in the next chapter. At this point, it suffices to see how we can generate populations with these distributions. Let's say, for instance, that we want to change our population 1 from a normal distribution to a uniform distribution. Then we simply comment this line here and we uncomment this line where we now define population 1 as a uniform distribution. Now this is generated in the exact same way as the normal distribution. We just have numpy.random and now we have .uniform instead of .random. Now the uniform distribution is a distribution where each value is equally likely to occur. The only parameters that we need to provide is this lower bound, which we put to 0, and the upper bound, which we put to 1. Now the size is of course again the amount of data points that we want to generate with this overall distribution. And the rest of the cell is exactly identical. Here we set the number of samples that we will take from each population. And this is the sample size, the number of data points in each sample. And the rest is all exactly the same. We don't have to change anything. So we can just run this cell. And now we see the same thing as before, but with a population that is clearly not normally distributed. Here, population 1 is uniformly distributed. It's just a large rectangle between the values 0 and the values 1. Now, even though population 1 is not normally distributed, the distribution of sample statistics is normally distributed, and it is centered around 0.5. Now, 0.5 is indeed the average or the mean of our population 1. And we can see this briefly by considering that this is a roughly symmetrical distribution. And thus, the average value will be the middle value. In this case, the middle between 1 and 0 or 0.5. And thus, we see for ourselves that the central limit theorem is also valid for populations that are themselves not normally distributed. And we can of course play around with it and take other distributions. Let's say for instance that now we don't want any normal distribution, but just two uniform distributions, one from 0 to 1 and the other one from 2 to 3. So we run this cell again, and we see, of course, the exact same thing. Two populations that are now not normally distributed, but nonetheless, their corresponding sample statistic distributions are normally distributed. Now, at this point, you might still object that this might be because we have population distributions that are symmetrical. Okay, so then we take a non-symmetrical distribution. Let's say the exponential distribution. Let's take population 1 to be an exponential distribution instead of a uniform distribution. Running this cell again, and it still amazes me that we can do this simulation with only a couple lines of code, and it is done within under a second. And we see the exact same pattern emerge. Even though the population histogram for population 1 is now highly unsymmetrical and certainly not normally distributed, the distribution of sample statistics is approximately normally distributed. So let's now look at a last example where we take two asymmetrical distributions. Let's say that population 2 is a Rayleigh distribution. So we have to comment out population 2 as being a uniform distribution. We again run this cell, and what we see is the following. And of course, exactly the same as before. So we can say that the central limit theorem also holds for populations that are not normally distributed. And this is why the normal distribution is so central to statistics and so ubiquitous. The central limit theorem says that you can have any population distribution that you can think of, the corresponding sample statistics distribution will always be approximately normal. That being said, the central limit theorem also has its limitations, and that is what we'll look at next by going back to the slides. In a nutshell, the central limit theorem is only valid when the sample sizes of each sample is sufficiently large. And again, you can check this yourself by going back to the code and changing some parameters. So let's do that. Here, the parameters that we're going to change now is the number of data points in each sample. At this point, we had 20, but let's now set it to 2. Now, before we run this cell and look at the resulting figures, let's think about what it actually means when we change this number. We are still going to take 10,000 samples, which we do in this for loop. But each sample will now only consist of 2 data points randomly sampled from our population. So the sample size will be 2. And if we run this cell and see what happens, then we clearly see that the central limit theorem breaks down, because these distributions that represent the sample statistics are not normally distributed anymore. In fact, they look more like the population distributions than they do like normal distributions. And this stays the same even if we change the underlying populations. Let's say that population 2 is not a Rayleigh distribution, but a uniform distribution, and we scroll down, then we see clearly that these are not normal distributions, and thus the central limit theorem does not apply. To fix this issue, of course, we can again put the sample size to be larger, let's say 200 in this case. If we take 200 data points for each sample, then we see again that our distribution of sample statistics are normal again. So the central limit theorem holds. Another way that the central limit theorem might not hold is that even though we have large enough samples, for instance 20 sample points for each sample, but we do not take 10,000 samples of each population, but only, let's say, 100. So again, now for each population, we take 100 samples, and each sample will have 20 data points. Let's look at the results. We see that the histograms representing the sample statistics are not nice and smooth, but they are nonetheless seemingly normal. In fact, the number of samples that we take for each population doesn't affect the results of the central limit theorem all that much as the sample size did. Of course, we want to fix this again, so we put the number of samples that we take for each population again to 10,000. and you can play around with these numbers yourself and see if you can break it in another way. Now, as a final remark, let's look at this last graph and what it actually represents. Now, as a reminder, this histogram showcases the distribution of differences between sample statistics. We got sample 1 coming from population 1 and we computed its statistic. Then we had sample 2 coming from population 2 and we computed its statistic. And then for these two statistics, we computed the difference. Now this we do for all of the samples that we took from our two populations. And all of these numbers together put in a histogram is what is showcased here. So why is this histogram that showcases the difference of sample statistics so important? What do we gain from it? Why is it useful? Well, let's see. First of all, it merges two histograms together. We had a histogram of the sample statistics of sample 1, we had a histogram of the sample statistics of sample 2, and now by taking the difference, we merge these two together. In effect, this histogram of the difference in sample statistics serves as the underlying mechanism for the p-value. Now, we will see the p-value in much more detail in later chapters, but it is well worthwhile to really understand this difference. And to see how it is helpful, let's go back to the code. And this time, what we will do is we will, for ease of use, again use two normal distributions as the population distributions. So we uncomment these first two lines, and what we will additionally do is that we will make them exactly identical. So we have two normally distributed populations, each centered around a mean value of 1, and they have exactly the same variance or standard deviation. So what will happen here? So we again take 10,000 samples of these two distributions. We again take 20 data points for each sample, and we run the simulation. So what this represents is that we take samples from the same underlying distributions, and therefore we expect that the distribution of sample statistics will also be the same. So the histograms on the second row will also be identical. Identical in an approximate sense, of course. They're both normally distributed and they center around 1. Now, because these underlying populations are identical, whether we take a sample from population 1 or we take a sample from population 2 shouldn't really matter. They are in a sense indistinguishable because they come from the same underlying population. So let's now say that you are indeed given two of these samples and you were asked whether these samples indeed come from the same underlying population. So what can you do in this scenario? Well, one way forward is to compute the mean of sample 1 and compute the mean of sample 2, and then subtract these two means from one another. Now, if these samples come from the same underlying distribution, then the difference between these sample means should be approximately 0, because the population means subtracted from one another are exactly 0. The population mean for population 1 is 1, and for population 2 the mean is also 1. But of course you're working with samples, random subsets of these populations, and therefore it will almost never be the case that the mean of sample 1 and the mean of sample 2 are exactly identical. Sometimes this difference will be larger than 0, and sometimes this difference will be lower than 0. And you can see where I'm going, of course. The difference between these two sample means is of course distributed. And this is exactly what we plot in this last figure. We plot the difference between sample means. Now, of course, thanks to the Central Limit Theorem, we see that also this distribution is normally distributed. And indeed, it is centered around the value 0. And in fact, if you then compute the difference of sample means of your specific two samples lies within the bulk of this distribution, then you can conclude that indeed your two samples come from the same underlying population. And this is the entire mechanism in a nutshell around the p-value. It all rests on the Central Limit Theorem. Now, if this reasoning wasn't immediately clear, you can either watch it again or you can wait for later chapters where we will again dive into the details of the p-value. And this brings us to the end of chapter 4, where we learned about the Central Limit Theorem. Now, we didn't learn about it from a vague definition or by delving into the mathematics. Instead, we learned about it by simulating it with generated datasets. And I hope by doing so, you will now have a more concrete and intuitive understanding of what the Central Limit Theorem actually means. Now, at the end of this chapter, we already looked at some different distributions, the uniform, exponential, and Rayleigh distribution. So in the next chapter, we will delve into more detail where these distributions come up and what we can actually do with them. So I will see you in the next chapter.